Welcome back to the next session, and I welcome you all again. Now we have our second speaker, Professor Mohammad Zaheer Khan Yusufza sir from IIT BHU. So here is a brief introduction about him before we begin. Before I ask him to deliver his lecture, Professor Mohammad Zaheer Khan Yusufzai sir is a distinguished faculty member in the Department of Mechanical Engineering at IIT BHU, Varanasi. He currently serves as professor and is also affiliated with the Main Workshop Administration, where he holds the position of professor in charge, Main Workshop. His academic and research specialization lies primarily in welding processes, welding metallurgy, friction stir welding, material characterization, and non-destructive evaluation techniques. Over the years, Professor Zaheer Sir has authored and co-authored numerally scholarly works on the topics such as microstructural characterization of welded joints, magnetic Barkhausen noise analysis, material response under various welding conditions, ultrasonic vibration assisted grinding, and life cycle assessment relevant to the advanced materials. Many of his articles explore the interplay between the manufacturing processes and material behavior under magnetic or thermal stimuli, reflecting his strength in the integrating material science and applied mechanics. For instance, he has investigated the magnetic hysteresis response of the welded steel, residual stresses assessment after friction stir welding, and the effect of eco-friendly lubricants during the grinding processes, and among other areas. In his administrative roles, Professor Zaheer Sir has been actively involved in workshop management and technical oversight, bridging the gap between the theory and the hands-on engineering practices at the IIT BHU campus. His contribution as a resource person in academic forums and FDPs reflect both his domain knowledge and his commitment for mentoring the faculty and students. Given his deep expertise in advanced functional materials, bending technologies, testing techniques, and process optimization, Professor Zaheer Sir is highly suited to lead sessions like this or the lectures in this FDP under the theme Towards Sustainability, the Role of Advanced Materials in Next Engineering. His work employing in non-destructive evaluation and microstructure analytics align well with his program's subthrust, particularly in assessing environmental impacts, life cycle behavior, and material sustainability. We are very privileged to have Professor Zaheer Sir with us, and his presence will undoubtedly enrich the academic discourse, spark insightful interactions, and inspire deeper investigation in this field. So now it's my honor to invite Professor Mohammad Zaheer Khan Yusufzai sir from the Department of Mechanical Engineering, IIT BHU Varanasi, to kindly share his expertise with us. So, sir, we are eagerly looking forward for your insightful and guidance. The virtual platform is all yours, sir. Thank you.
Thank you very much for a generous introduction. Uh, and I would like to thank the organizing committee, the head of the department, the director of the institute, to have given me this opportunity to talk with the audience that is present today in a virtual mode. So, one more thing, I especially liked the timing in the sense that generally we are quite busy with our academics and research during the daytime. So it is a wonderful idea thought by the institute that they have organized this in a wonderful time schedule. So I'll share my screen first. Uh, there was some issue, I think.
No problem, sir. We can wait.
Wait. Yeah. So, is my slide visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. And is it moving to the next slide also?
Yes, sir.
Okay. So, thank you very much. So, first of all, I would like to thank the KIPM Institute at Gorakhpur for giving this opportunity to talk with you on the topic of recent development in cladding techniques in the FDP towards sustainability, the road of advanced material in next generation engineering. Uh, so, without taking any of your further time, I would like to introduce the topic that I have decided to talk today, that is on cladding. Now, why cladding is important? Now, wear and corrosion, they significantly impact the India's economy with the loss that is spanning various sectors. So, as we all know, most of the engineering components and structures, they are made up of metals and alloys. These metals and alloys, although they possess wonderful properties, but they are also likely to get corroded. So all the metals and alloys, they are basically extracted from the earth crust in form of ores, which is the more stable form of the material, that is the metals and alloys. But we all know that we hardly can use ores for any purpose, so we basically refine it, make it pure metals, then we add some additives to the metals and convert it into alloys. These metals and alloys are used in various sectors like manufacturing, petroleum, oil and gas, power sector, transportation, mining and agriculture equipments. And in all those cases, they are used in a refined form. But over the period of time, two things commonly happen to the material that has been used for these mechanical engineering applications. One and the foremost is corrosion. So most of these engineering metals and alloys that are used in these sectors, they are continuously in contact with the environment, and over the period of time they get react with the oxygen that is present in the atmosphere, and this oxygen leads to the materials again trying to convert into the more stable state, that is the oxides. Now, this conversion of material into oxides leads to the loss of the material, and it is one of the major problem that is being faced by globally also and in India also, because with the corrosion, the material gets lost, its properties are deteriorated, and in many cases its functions are also hampered. Another problem that is commonly encountered is that if the material is in contact with a medium which is trying to remove the material in small bits and pieces, then also there is a loss of material. This is very common in the case of moving components, but otherwise also in structures where small sand particles or any other mechanism can actually remove materials in small pieces, and that accounts to what is known as wear. So because of these two issues, there is a tremendous loss to the economy, and this has been tabulated over here. As you can see, in the manufacturing sector, the annual loss is 4.2 lakhs crores. In the petroleum and oil gas industries, the loss is to the tune of 1.5 to 2 lakhs crores, because many of the times the components are safeguarded against corrosion. Power sectors, again 1.2 to 1.8 lakh crores, because of the corrosion that is taking place in the boiler tube, turbine blade wear, and transmission failure. Similarly, in transportation, including railways and highways, there is a loss of 2 to 3 lakhs crores, majorly because of the bridge collapse, rail track degradation, and vehicle component corrosion and wear. The mining and agriculture sector, which is also very important sector in the case of Indian economy, they also undergo significant losses corresponding to approximately zero point 0.8 to 1.2 lakh crores per year. These losses are primarily because of the equipment wear in the abrasive environment and the corrosion of the agriculture system and the machineries that are being used for in the agriculture and mining sector. So you can see that lot of waste is going on because of this corrosion and wear that happens in the metallic components that has been made for engineering application. These are some random photographs that we have collected from the internet, and you can see that in most of the cases, as you can see, that the corrosion has occurred and the surface of the material has been damaged and its functionality has been reduced. In many cases, as you can see, there is a bridges that has been made, and because of the corrosion, the strength of the material has get lost, and either this bridge will become unserviceable or may even catastrophically get collapsed also. Similarly, you can see there are buried pipelines that have undergone corrosion and now they are completely rotten up and they cannot be used. Similarly, there are other components like in figure number C, you can see a turbine blade that has undergone wear. Then there is a jet engine turbine blade, and again the petroleum industries where various components have undergone either wear or corrosion or a combination of corrosion and wear. These damages that have done will lead to either the components getting discarded or in some cases catastrophic failure can also occur, leading to loss of human life and property. So these corrosion and wear are great damages that has to be done. So what we have to do is that we have to do something about it. So what we can do, as I have mentioned, the materials that we are using are bound to get corroded. So there are two solutions that are available. One of the solution is that either we use a material that itself is corrosion resistant, that is those metals and alloys that don't rust. So generally what we see is that those materials that are corrosion resistant, that don't rust, they are generally expensive materials, and these expensive materials are not only expensive because of the raw material cost, but these expensive material are also difficult to manufacture into the components and products that we are desiring to make. So, and second an important thing is that why at all use an expensive material when this corrosion basically affects only the surface part of the material. So let us say we have got a component that is corroding. If we can do something to the surface, then the surface will not corrode and underlying material automatically gets prevented from corrosion. So we can do something. Similarly, if we talk about the wear, then the wear also is a surface phenomena and it happens on the surface of the material. When two surfaces are rubbing against each other or some fine particles are impinging on the material, they are actually initially damaging the surface of the material. So if somehow we can change the surface of the material, even though the underlying material is cheap, then all those benefits that is derived from an expensive corrosion resistant and wear resistant material that can also be extended to by to the cheap material. So the surface coating of steel components, if it is done by a corrosion resistant material, then let us say it is able to extend the service life by 3 to 5 times. Then the replacement cost is also reduced by some 40 to 60%. Similarly, in different sectors like oil and gas, the pipeline and the valves can be protected from acidic environment by and thus preventing a leak by coating these components or from the inside and outside. with a corrosion resistant material. Similarly, in power plants, if we perform surfacing, then it enhances the boiler's tube durability, reduced any shutdown that may be that may be necessitated because of the boiler tubes getting damaged. Similarly, in transportation engineering, the rail tracks life can be expanded, the bridge lifespan can be extended, and the overall maintenance cost can be directly reduced. Now, any component, if it is replaced, then then it will involve complete reworking and completely making a new product. So this manufacturing of a new product comes with its own share of carbon emission, and this greatly impacts the environment. So if we are reducing the replacement and repair, then there is a significant reduction in the CO2 emission in total, and therefore it has been estimated that the steel production which is there, it contributes to 10% of the global CO2 emission, and therefore if the need for replacement with new steel can be reduced, then a significant chunk of this 10% of the global CO2 reduction can be addressed. Countries like US, EU, they save 15 to 35% of the corrosion cost through advanced coating and management system. So they already are using this process of making the components corrosion resistance by techniques known as cladding and hard facing, and in this turn they are saving 15 to 35% of the cost that we are wasting in form of corrosion and wear. So what is surfacing? So surfacing basically refers to the technique of depositing a material over a base material or a substrate to impart some desired properties to the surface that is not intrinsic to the underlying material. So that means if we have taken a piece of material, then it will have some intrinsic properties. If by some method we can deposit another layer of material on the already chosen material such that its surface properties are altered in a desirable fashion, and those properties which were not inherently present in the material can be imparted on the surface of material, this is what is basically known as surfacing. So if you can see in this diagram that is there, so this is a substrate material. Let us say it is having certain mechanical properties that are essential for making a component, but let us say it lacks certain properties like it is not corrosion resistant or it is not wear resistant. So this property of corrosion resistant and wear resistance can be brought about by depositing this material with a layer of another material, and this material that has been additionally deposited will have those desirable properties, like if corrosion resistance is required, the deposited material will be corrosion resistant. If wear resistance is required, that deposited material will be wear resistance. So depending on the application or the desire of the surface properties that is required, the process of surfacing can be divided into several types. The first type is known as hard facing, where a wear resistant layer is deposited on the metal component and thus increasing the component's resistance to wear and tear or cavitation, and thus makes it long lasting, and it performs better in surface. If the same top layer that I have shown in this diagram is applied with the primary objective of giving corrosion resistance, then the process of depositing a layer of material on the substrate will now be called cladding. Now, there's no much difference as far as the process is concerned, only with the choice and selection of the deposited material, the term changes. So, if the choice is to make a corrosion resistant layer, The same process is known as hard facing. If the choice is to improve the corrosion resistance of the material, the process becomes or is called as cladding. So primarily, as I have told you, that surfacing is basically used to create or deposit material with the objective of improving the properties. So these are the two properties that need to be improved, and they are commonly used in industries. Apart from that, sometimes because of the wear that has taken place or because of some shortcomings in the manufacturings, a component that has been produced has lost its dimensions. That means if there is a piece of material, let us say it is in a cylindrical shape, and it was desired that its diameter should be 50 mm, because of some reason, either wear or because of some issues during the manufacturing process, let us say its dimension becomes 48 mm. So this 48 mm component, cylindrical component, will not cannot be used because it will not provide the sufficient strength and force resist or and the capability of bearing the load, and therefore it is generally discarded. But what we can do is that we can apply the same process of surfacing by depositing additional material on on the substrate material, and this additional material that is deposited is having exactly the same properties as the substrate material. So here in this diagram, let us say this is a substrate material and this is a deposited material. So in the case of increasing the dimensions, the properties of the substrate material and the deposited material should be same, and in that case the process will be known as a build up process. This build-up process is also sometimes used to perform selective deposition of the material, and then the process can be used to perform what is known as additive manufacturing. It may also be sometimes your choice that if the material has gone through wear and you want to build it up, you can build up with the same material by going for the process known as build up, or you can deposit a hard faced material, a wear resistant material, and do hard facing also. When you are doing the hard facing, the compensation in the dimension can also be taken up, and additionally, the material now will be wear resistant. Similarly, sometimes when you are joining two materials, it is desired that the surfaces that are brought in contact, and if they are not compatible with each other, then the surfaces can be coated with a layer of a third material, and then joining of the material or dissimilar material is taking place. In such situation, the process is known as buttering. To give you an example, let us say we are interested in joining mild steel with stainless steel. So if mild steel is joined with stainless steel directly, then mild steel has got higher percentage of carbon. Stainless steels generally have got very low percentage of carbon. There will be carbon migration taking place from the mild steel to the stainless steel side. The carbon that has migrated to the stainless steel side will actually react with the chromium to form chromium carbide, and the stainless steel will get sensitized or it is likely to get corroded. So in this case, the components before they are to be joined, a third material generally inconel is deposited on the stainless steel, and when inconel is deposited, there is sufficient amount of chromium, the phenomena of sensitization will be prevented even if some carbon is migrating. So this is another process of surfacing known as buttering. Now let us talk about cladding. Cladding is, as I have defined, it's a deposition of the material layer on the component surface to increase its corrosion resistance against hard environment. The cladding material actually acts as a barrier between the substrate and the corrosive environment. The cladding that we have deposited can be either a thin cladding or thick cladding. Thin cladding is also known as film cladding. These thin claddings are generally few microns in dimensions. Maximum it can be 1,000 microns, and they are generally carried out by processes like electroplating, physical vapor deposition, chemical vapor deposition, And these coatings, being thin, they, they will act as a barrier, but if there is any problem that has happened to this thin coating, if it gets peeled out, if it gets scratched out, then very easily the underlying material will be exposed and corrosion of this material will take place. So as an alternative, we can also deposit a thick coating, okay, that can be ranging from 1 millimeter in thickness to several order of millimeters in thickness. For this process of thick cladding, we cannot use physical vapor, chemical vapor, or electroplating as a method because it will be very, very time consuming if you want to develop thick films by these processes. So, arc welding processes, explosive welding process, laser cladding process, and thermal spraying is what is generally used to deposit the thin cladding. There are several constraints when we are performing cladding. One and the foremost constraint is the difference in the properties that is there. Generally, the cladded material is a different material and the substrate material is a different material. When we say that they are different material, we all know that the primary difference is in their corrosion properties, and the substrate material is likely to get corroded, whereas the clad material is such material that don't get corroded easily. This is the desired difference in properties. But then whenever we choose two different materials, there are a lot of undesired differences in the properties, like they will be having different thermal properties, they will have different coefficient of thermal expansion and contraction, there will be difference in their physical properties, that is their densities may be different, their weights may be different, their metallurgical properties, their mechanical properties may also be different. Now, these thermal, physical, and metallurgical properties being different becomes very difficult to join these material in form of a cladding. Second important thing is that we have gone to this alternative of cladding was basically to save cost. We wanted to offer a cost effective solution because otherwise, if cost saving is not there, we could have directly used a material that is itself or throughout corrosion resistant. But remember, we have said that a material that is throughout corrosion resistance is expensive, and therefore we have gone for cladding. Now, if this cladding itself is not cost effective, then it is not justified. Let us say we want to make a component and the component is cheaply made by mild steel and it is, let us say, costing $100, and the deposition of the material is costing, let us say, another $20. So the entire cost of the component after cladding will be $120. But let us say the cladding cost is very high and the material costs $100, material and manufacturing, and the cladding itself costs, let us say, $200. So the total cost will be $300. But if you make the component entirely of stainless steel, let us say it is costing only $250, then cladding is not justified in this case. And therefore, the cost of the cladding should be low so that it justifies that we can use cheap material and a cheap cladding process. The desired performance, that is the essential properties, that is the cladding should not only perform well, but it should not alter the performance of the component. So when we are depositing a material, we should also ensure that the underlying material that is behind this on which we have deposited the material, it should not undergo any adverse changes. Let us say we are depositing a stainless steel on top of mild steel, then this deposition process of cladding should not make the mild steel weak. So because if it becomes weak, then it will not be able to sustain the loads that it is desired or it is expected to sustain. So that is another thing or constraint in the case of cladding process. There are several processes that are used for cladding. So I will explain two of those processes in this lecture. But apart from those two that I will be discussing later, there are other processes also that are going on. You can see the first figure over here. This is basically what is known as gas metal arc welding cladding. So we all know that in gas metal arc welding process, there is already a filler material that is acting as one of the consumable electrode, and a welding arc is made between the substrate and the filler material. In this particular case, the filler material that will be used will be made up of a corrosion resistant material. And in this particular case, let us say for an example, we want to clad stainless steel on mild steel, then the material that is the substrate material will be mild steel. The filler electrode that is used in GMW will be made up of stainless steel. So when welding is performed, this filler material will melt in the arc, and it will get deposited on the substrate, thus successfully depositing successive passes of GMAW process can completely cover a layer of substrate material with the stainless steel. Similarly, for other arc welding process like GTAW process can also be used. Can you hear me?
Yes, sir.
Okay, okay.
Yes, sir.
Just I wanted to be sure. Okay. So, similarly, another process, a wonderful arc welding process, that is GTAW, can also be used. GTAW process is characterized with a very stable arc and a very clean weld that is produced. So, as you can see in this figure, there is a GMAW torch, an arc is produced, and a wire of the desired material is being fed. It is melting in the arc, and it is deposited on the substrate. So underline you can see substrate, and on top of it you can see round spherical layers of stainless steel or any other clad material has been deposited, and in this way again you can perform cladding. There is another process known as thermal spraying that is also can be used. So here you can see that there is either an arc, or in this particular case a plasma is there. So an arc is initiated between the positive terminal and the negative terminal housed inside your torch. So an arc is produced, and that arc that is produced is rushed through the input of this gas, and it is coming out in form of a jet. So so this jet that is coming out, it is coming out at a velocity, and then there is a small hole that is created over here. So when this is coming out at a high velocity, there will be a negative pressure or a vacuum that will be created, which will be sucking the powder inside. The powder will melt in form of tiny droplet. It will be propelled through this gas, and it will be depositing on the substrate in this form. So this is another thermal spraying process that can be used. All the three processes that I have discussed now are actually fusion based processes. Apart from this, we can also use explosive welding for performing cladding. So as you can see in this figure, this is the metal that is written at the bottom. This is the substrate. This is the clad layer of brown color that, as you can see over here. So before starting, there's a standoff distance that is created between the clad layer of metal and the substrate. The clad layer of the metal is covered with a layer of explosive. The explosive is burnt. Once the explosive is burnt, it will be pushing the clad layer at a high velocity towards the substrate. The high impact of the clad material against the substrate will deform the both material, and it will lead to solid state bonding taking place between the clad and the substrate material. In this way, again, in a solid state welding, in a single go, you can deposit a substrate layer with the clad layer. So this is a small result that we are showing. In this case, we have deposited a layer of copper on mild steel substrate using gas metal arc welding process. The substrate was of mild steel. It was made as one of the terminal connected to the power source. The electrode in GMAW process that was used was of copper. So the copper electrode was passed and an arc was established between the copper electrode and the mild steel substrate. And this you can see successive layers of copper has been deposited on the mild steel substrate. Of course, whenever we are using these different dissimilar combinations, we have to do a lot of trial runs, and this is the photograph of the trial runs that were carried out, where the process parameters were optimized so that we can produce clad layers of sufficient quality. When we are performing this experiment of depositing copper on mild steel using GMAW process, then several challenges occur. As you can see in this bottom diagram, when CO2 was used as a shielding gas, then lot of spatters were occurring, and although beads could be established, but because of the spattering, the surface became very rough and it was hardly any use. When little bit of uh, argon was mixed with the carbon dioxide, so one of the student worked on this and he made a small setup where CO2 and argon could be actually mixed and fed as a shielding gas. Then the amount of spattering was less and we could successfully deposit copper on top of the mild steel substrate. So just to have a look as to how this clad layer has been performed, the plates were cut as shown in this figure and their cross section was examined. So if you can see this cross section, this is the substrate of mild steel, and here on top you can see copper has been deposited. One thing that you will immediately agree is that a very uniform and thick layer of copper could be deposited on mild steel. But what is significant over here to note is that there are a lot of porosity that are present. So the clad layer, although could be formed properly, it has led to formation of lot of porosity, and therefore this is problematic. Another process that is commonly used and we also using it regularly is laser cladding. So laser cladding is basically an additive manufacturing process where laser is used to melt the material and the coating material both, and they can be deposited for cladding purpose also. Apart from performing cladding, this can also be used for the repair of the micro cracks that are present on the surface. It can also be used to reinforce or build up components that have worn. It can be naturally used for prevention of corrosion and wear, that is cladding and hard facing, and this can also be used to customize the surface property of the material, that is you can have a combination of powders where you can impart both corrosion resistance and wear resistance. In laser cladding process, a laser heat source is utilized to deposit a thick layer of generally zero point 0.5 mm, so to more than 2 to 3 mm of metals or ceramics known as clad on a solid substrate uh, through this process. So you can see in this diagram, there is a laser light that is coming. It is producing liquid intense heat. This intense heat, wherever it falls, it will melt the substrate material. Additionally, we can feed powder through this, and these powders that are falling at the point, they also get melted, and this melted powder and the substrate, they together combine and form a clad layer on the substrate. There are several potential applications of laser cladding. So it can be used for the restoration of the gears. So the gear surface that have worn out and the bearing surface that have worn out, they can be actually restored by depositing a layer of material. They can be used for hydraulic rod enhancement in the hydraulic components. They can be used for the repair of turbine blades. They can be used also in the aerospace upgradation. And in total, they will be reducing the high cost of replacement, and therefore it's a very much potential process. So this is basically the fundamental of the laser cladding system. Laser cladding is also known as laser metal deposition, uses a focused laser beam to melt and fuse a layer of coating material. The coating material can be either in form of powder or in the form of wire, which is put on the substrate. This enhances the surface properties like wear resistance, corrosion resistance, increase the hardness, or this can also be used for the repair or repair of worn and damaged part. The core components of the laser cladding system is a laser source. The laser cores can be many. It can be either a solid state laser, it can be a fiber laser, diode laser, or CO2 laser. Only thing is that the power of the laser should be sufficient to melt the material and sometimes even the ceramics. There should be a beam delivery and optics. So whatever laser is there, it is coming in form of a beam. This beam, to enhance its capability to melt the material, should be focused to a point, and for that you need a beam delivery system and the optics. Basically, they are in form of lenses. Now, this melting has to be accompanied with powder. So, there should be a powder or a wire feed system. So, the material that has to be deposited can be in form of a wire, but generally it is in form of a powder. And this powder or wire is to be fed. And of course, since the entire surface of the substrate has to be covered, so there should be method by which this the laser source and the powder can together move. The key process parameters are laser power, scanning speed, that is the speed at which the laser is being moved in the X and Y direction, the powder feed rate, beam spot size, and shielding gauge flow rate. These are four different methods by which additional material can be fed during laser cladding. One of the easiest method would be to pre-place the powders. So the powders are pre-placed on the substrate and the laser beam is simply made to fall on the substrate with the pre-placed powder, and the process of melting and solidification follows. The second method could be that the powder is fed coaxially, that is, the powder is being fed off in all the directions. So there is a central portion through which the laser beam is coming, and all along on all the sides powder is being fed. There can be an off-axis powder system where the powder is being fed separately and the beam is actually following it and depositing the powder and the substrate. Similarly, wire can be also fed and the wire can be made to melt and get deposited. It is interesting to note that the wire feeding is generally done in a off-axis type of a system. This is the experimental setup that we have got in our lab. So there is a chiller because a lot of heat is being generated during the lasing operation. Most of the heat energy that is given, only a part of that energy actually comes out in form of a laser, and most of the other energy that is given, it converts into a heat. So we need to have a very effective chiller to cool our lasing system, that is the laser source. Apart from that, you need cooling pipes to protect your components, that is your cladding head, from getting damaged because of the laser. Similarly, we have got in this figure, you can see this is the main lasing head, laser head that is used. You can see that we can feed powder from these four sides. Inside this vertical tube, there are optics placed, and the laser will be coming at this end. The powder will be also coming through this nozzle and getting deposited. There is a separate powder feed system that is attached to the machine. So we can actually use not one but more than one type of powder. The powder can be mixed also in this power feed system, and it can be fed through the laser cladding head and deposited. Generally, most of the material and the components need to be protected against reaction with the atmospheric gases. So argon is used as a shielding gas. But most importantly, this argon is also used as a carrier gas to make the powder flow from the powder feed system to the cladding head. So this is how the powder looks like. And let us say in one of the example, an high entropy alloy powder was used. So you can see that it is having equimolar content of iron, cobalt, chromium, nickel, and molybdenum. So it's a 5 system HEA powder that has been used. And with EDX, you have to always confirm. The SEM will tell you whether the morphology is round or not, because these morphology affects its melting performance. So, before any such experiment is performed, a single clad characteristic of the cladding has to be obtained. For this, a series of experiments were performed. So, what happened in this series of experiment is that uh, we took a chosen powder, and we just made one single bead using the powder that is being used. So the laser head was moved on a plate from one end to the other end of the length of the plate, and a single bead was obtained. This bead was actually cut across. When it was cut across, it looked like this, and this is the bead that we obtained after we have cut it and polished it. So after polishing, you can see there is a clad bead that is obtained, and the remaining portion is actually the substrate material. So, for any proper characterization, it is important that these parameters of the bead characteristic bead profile should be noticed. The important characteristics is what is the depth of penetration or depth of melting that has taken place, what is the height of reinforcement that is created, that is basically corresponding to what is the thickness of the clad layer that has been obtained, then what is the width of the clad layer that has been obtained, what is the extent of damage that has been done to the substrate in form of an heat affected zone, and ultimately how this is performing. So micro hardness of the bead can be taken as one of the parameters. So these type of experiments are performed. In this particular experiment, one of the student performed this experiment and deposited the clad single layer of clad in 16 different combinations of laser power, scan speed, and powder feed rate. And then these clad width, clad height, clad depth, heat affected zone thickness, and micro hardness. And apart from this, the dilution was calculated as this. So all these plates were actually cut across, and the measurements of clad width, clad height, dilution, the thickness of the heat affected zone were measured, and after measuring, it has been tabulated like this. So at different process parameters, different values of clad height, clad width, heat affected zone is obtained, and clad height and clad width basically dictate what is the extent of dilution that we are obtaining in this particular case, and consequently this is reflected in form of change in hardness of the material. So I'm just ending this part with this, that the clad height and the clad width, and if proper bonding is not there, proper melting is not there, this type of problem may occur. Whereas if the process parameters have been optimized, then this type of a clad layer is obtained, and subsequently several such clad layers can be deposited to cover material, substrate material with the clad. Now, this is again Laser cladding is again a a fusion based technique for deposition, and this has got an inherent problem, and that inherent problem is that whenever I am depositing a layer of substrate material, a layer of clad material on the substrate material, it is essential that some amount of substrate material should also melt. If the substrate material does not melt, as you can see in this left hand figure, then the clad material will not be firmly anchored or joined with the substrate material. And with the application of force, this clad layer will simply peel off. Whereas if we want good anchoring, then what is going to happen is that some substrate material is also going to melt. When the substrate material also melts and the clad material also melt, in this particular clad, they will be actually mixing. So as you can see, this much is the amount of the deposited material. This is the amount of the substrate material, and therefore they will thoroughly mixed within the liquid state. And the material that is this solidifying is actually a combination of substrate material and the clad material. So this clad material, which we wanted, let us say of high entropy alloy, will now have large amount of iron or mild steel also added to it. Similarly, if you are depositing a stainless steel powder, then this stainless steel will get mixed with iron, and the composition of the clad will be actually largely in between the composition of mild steel and stainless steel. And in this case, it may not offer the desired property as it is desired from a clad layer. So it is important that mixing of the clad and the substrate should not take place. And friction stir welding is another technique that has been used to deposit a layer of clad material on this process. So how much time is remaining? Let me check. Oh, it's already 9. So I'll just finish in 15 minutes quickly. So this is this friction stir welding is a solid state low heat input joining process. It was developed recently in the sense that it is one of the new processes. It is developed in 1991 and it offers most of the advantages that are there in the solid state welding process. So these are the list of the advantages. That is, it produces defect-free joint or clad. It improves the mechanical property. It is highly productivity. It's a simple process, repeated when consistent. Does not require skilled manpower. Has good surface finish, and it can be used for positional welding and cladding. So friction stir welding and friction stir surfacing or friction stir cladding is not much different. Everything is same. The machine is same, the tool is same. Only difference is that the pin is of a shorter length than the thickness of the workpiece. In fact, the the thickness of or the length of the pin is corresponding to whatever is the thickness of the material that has to be affected. And just like in the case of other cladding processes, here several passes of friction stir welding has to be carried out to completely bond the surface, the clad material with the substrate. The good thing is it's a solid state welding process, so no mixing of the substrate and clad material will take place, and the material that we are depositing will remain relatively pure. So this is how several passes are made. So let us say there is a clad layer, and on top of it there is on a substrate is a clad plate that has been pushed. So overlapping passes are made like this, and the entire plate can thus be covered. And if required, then little bit of machining can also be carried out. So this is the first experiment that we have carried out. In the first experiment, we have deposited a layer of copper on the aluminum substrate. And in the other set of experiment, we have deposited a layer of copper on the top of mild steel substrate using multiple friction stir welding passes. So just like any process is difficult, here also we face lot of difficulty. The process parameters, if they were not optimized, In the case of cladding of copper with aluminum, there was melting of the substrate, as you can see over here. And in the case of welding of mild steel on copper, there were defects like shoulder void, excessive flash, and other defects were there. So after several trial runs at the process parameters listed in the table, we could successfully deposit a layer of copper on the top of mild steel substrate at a tool RPM of 700, at a tool translational speed of 100 millimeters per minute, tool tilt of 1.5 degrees, shoulder diameter 20 millimeters, pin diameter 6.5, and the pin length was kept 3.5 because the thickness of the clad layer that we are trying to deposit was 3 mm. Then the other part was how to select the offset distance. So this schematic will help you. If we are performing friction stir welding, then this parabolic zone of stir is created, and this stir zone is actually known as the weld nugget, and the width of the weld nugget at the interface of the clad, and this demonstrated by this arrow. So the maximum offset that we can give is actually equal to the to this distance. If any more offset is there, then there will be unbonded portion that is remaining. So similarly, several trials were carried out, and it was found that a particular distance of 8 mm offset was sufficient. If more than 8 mm was given, then there were unbounded region, and if very less amount of offset was given, then unnecessarily lot of welding passes has to be carried out. So this is the radiograph of the cladded plate that has been produced. As you can see, if the parameters were not right, these defects can occur, and you can see this is a defective plate, and this one is a defect-free plate. No defects are actually obtained. This is the microstructure and macrostructure. You can see very firmly the mild steel and the copper plate has been anchored. This is not only macroscopic bulging that has anchoring that has taken place, but as you can see at the magnified level, there is microscopic bonding that has taken place between the two material. But what is important to note over here is that the mild steel is not mixed with the copper on the top layer. Then, of course, some mechanical tests were performed, like hardness was carried out, tensile testing was carried out, bend test was carried out, and this is the result of the bend test. After the plate has been cut and it was bent in a tensile testing machine, you can see even after bending in all the three directions, no disbonding is actually taking place. This is the SEM analysis, and you can clearly see on the top portion, even in the mapped index, it is only mostly consisting of copper. In the bottom portion, it is mostly consisting of iron. So no mixing of the material has taken place, although there is firm anchoring of this that has taken place. This is the result of the tensile test. This is the tensile test result of copper. This is the tensile test result of the mild steel. And as expected, the properties of the copper coated mild steel is lying in between the properties of copper and mild steel. It was very much expected. What was slightly disappointing is that the ductility of the overall ductility slightly fell down from that of the mild steel. This is these are the factograph, and this is the comparison of the yield stress, percentage elongation, and ductility of base copper, base steel, and copper cladded steel. This is the SEM image, SEM and mapped EDEX image of the fractured sample, and you can see even during the tensile testing process, there is no transfer or not much transfer of copper into steel, and most importantly, iron into copper. This I have already shown you. This is another development that we have carried out. So as you remember, when the mild steel was deposited, mild steel was covered with a layer of copper using gas metallic arc welding process, there were a lot of porosities. So another set of experiment has been carried out where this porosity has been filled by performing friction stir cladding on top of friction stir pass has been made on top of this, and so see wherever this friction stir process is done, the porosity has been removed. So that's all from my side. Thank you very much.
Thank you very much, sir. So, are there any queries from the participant side? Okay, so I guess there is no query. Thank you, sir. Thank you for sparing time from your busy schedule for all of us.
Thank
Thank you
you.
very.
Thank you. I can disconnect now.
Yes, sir. Sure, sir. Okay,
Okay.
thank you, sir.
Thank you very
Thank you,
much.
thank you.
Thank you so
Yes.
much.
It's It is my privilege to extend our heartfelt gratitude to Professor Mohammad Zaheer Khan Yusufza sir from IIT BHU Varanasi for delivering an insightful and enriching expert talk on recent developments in cladding technology and sparing time from his busy schedule for all of us. Sir, your presentation offered valuable perspective on the latest research trends, innovative techniques, and practical application of the cladding processes in modern engineering. The depth of your knowledge, coupled with the clarity of your explanations, has truly enhanced our understanding of this evolving field. And this session has inspired our participants to explore new directions in materials engineering and sustainability, aligning perfectly with the objectives of our faculty development program. So, on behalf of organizing committee and all the participants, I sincerely thank you, sir, for your time, effort, and valuable contribution for the success of this FDP. And with this, we come to the conclusion of the day one of this faculty development program on towards sustainability, the role of advanced materials in next generation engineering. I extend my heartfelt gratitude to our esteemed speaker for the today's sessions, Professor Zaheer Khan Yusufzai sir from IIT BHU and Professor Om Prakash sir from NIT Patna for their insightful and enriching sessions. I also thanks all the participants for their active engagement and patience throughout the day. Now we look forward for your continuous participation and enthusiasm in the upcoming sessions as well. Thank you all once again. Have a pleasant evening, and the feedback from this session will be shared in the group, so you can go through all of that again. And have a great day. Let's call it a day. Good night, everyone. Good night, sir.
Thank you. Thank you very much. Good night to all of you.